NASA pointed a camera at what it thought was just another moon, and Io answered with something so violent. It broke their idea of how a rocky world is supposed to work. This video's the story of what NASA actually found there. The eruptions, the data, the "this can't be right" moments, and why Io is still the one place in the solar system that refuses to fit the rules. How can the most violently active world in the solar system be a small yellowish moon parked next to Jupiter, only a bit bigger than our own moon? You're looking at Io, a body only about 3,640 kilometers across, with a radius of roughly 1,822 kilometers, orbiting Jupiter about 422,000 kilometers, around 262,000 miles. It spins once every 1.77 Earth days and always shows the same face to Jupiter, just like our moon does with Earth. On paper that sounds simple, even boring, just another small rocky moon in a big planet shadow. In reality, it is the opposite of quiet. So how did we go from probably a cold, cratered rock to this thing is the most volcanic object we've ever seen? When NASA's Voyager spacecraft passed the Jupiter system in 1979, the expectation was very conservative. Small rocky bodies were assumed to cool down quickly. The standard picture said, if you're small, you lose heat fast, you freeze, and you go geologically dead. So scientists expected Io to look like our Moon or Mercury. Lots of impact craters, some old lava plains, maybe a few tectonic cracks, but nothing moving anymore. The cameras were ready to document an old stable surface. Instead, they caught an eruption in progress. Near the edge of Io's disk, in Voyager 1 images, there was a strange bump sticking out into space. It wasn't a mountain, it was a plume, a huge eruption shooting material hundreds of kilometers above the surface. When the team checked more frames, they found multiple plumes. That one moment flipped the story. Io was not a frozen fossil, it was violently active. Follow-up analysis plus later missions like Galileo revealed more than 400 active volcanoes. For a body smaller than Mars and only a bit bigger than our moon, that number is extreme. But hearing volcano might make you think of something like Hawaii, slow lava flows, maybe a tall cone. So the next question is, how strong are these eruptions really? And how far do they push the limits of what we see even on Earth? On Io, some eruptions drive fountains of gas and molten rock that can reach from tens to hundreds of kilometers high. In the most intense cases, plumes can climb to around 500 kilometers, about 310 miles, above the surface. For comparison, that is higher than the cruising altitude of any airplane, and not far from the region where many Earth satellites orbit. These eruptions are not just local hill-sized events. They inject material into space, then let it fall back, covering areas hundreds of kilometers wide with fresh deposits of sulfur and other material. In terms of sheer height and area, they beat anything we see on modern Earth. If eruptions are that big and that frequent, what happens to the crust over time? Does the surface keep its shape, or does it get constantly rebuilt? The answer is that Io keeps erasing and rebuilding itself. Lava flows can stretch for hundreds of kilometers. Fresh dark flows spread out, then get coated by brighter sulfur dioxide frost. Massive depressions called Patera flood and refill. Mountains slump and sometimes collapse along steep cliffs. Impact craters, which should accumulate over billions of years, are rare, because new material keeps burying them. When scientists estimate the total heat flowing out of Io, they get values roughly 2 to 3 watts per square meter on average. Earth's global average is about 0.08 watts per square meter. So per square meter, Io is pumping out about 20 times more internal heat than Earth does. That is why the surface looks geologically young almost everywhere you look. On Earth, that kind of heat flow would be catastrophic if it were spread everywhere, but our volcanism is mostly confined to plate boundaries and a few hotspots. Io has no plates moving around like Earth's. Instead, the intense activity is happening across a relatively simple continuous crust. This raises a direct question. How does a small moon maintain such a ridiculous heat budget for billions of years, when a bigger, more massive planet like Earth is comparatively calm? On our planet, the main energy sources for volcanism are leftover heat from formation and the decay of radioactive elements in the mantle and core. That internal heat drives convection, moves tectonic plates, and occasionally ruptures the crust in volcanic eruptions. Io is too small to hold on to that much primordial heat for this long. If it worked exactly like Earth, it should have cooled and mostly shut down a long time ago. The observed activity forces a different conclusion. The dominant engine inside Io is not just radioactivity, it is gravity, specifically tidal heating. Jupiter's gravity pulls on Io strongly, but the key detail is that the orbit of Io is not a perfect circle. It is slightly stretched into an ellipse. That means the strength of Jupiter's pull changes over each orbit. When Io is closer, the pull is stronger. When it is farther, the pull is weaker. The whole body gets flexed by up to around 100 meters, over 300 feet every orbit. Think of that as taking a solid rock sphere and repeatedly squeezing and relaxing it. The rock resists that change, internal friction builds up, and that friction turns orbital energy into heat. You might ask, why doesn't the orbit just settle down, become a circle, and stop all this flexing so the moon can finally cool off? That would be the logical end state if Io were alone, but it is not alone. It is locked in a gravitational resonance with Europa and Ganymede. For every orbit Ganymede completes, Europa goes around Jupiter twice, and Io goes around 4 times. This three-body lock keeps Io's orbit slightly eccentric instead of letting it circularize. In other words, the other moons are constantly pumping more energy into Io's orbit. Jupiter's gravity keeps squeezing it, and the interior keeps turning that into heat. This is why Io forced scientists to accept a new type of rocky world, a tidally cooked body where orbital mechanics, not just radioactive decay, dominate the energy budget. The same physics that quietly raise tides in Earth's oceans are, in the Io-Jupiter system, powerful enough to melt rock on a global scale. That shift in understanding is not just about one moon. It affects how we think about rocky exoplanets packed close to their stars, and about other tightly bound systems where small bodies may be far more active than their size suggests. So now there is a new, sharper question that pushes the tension higher. If tidal forces are doing all this, exactly how does that gravitational rack work in detail? How much power is really being dumped into Io's interior? And how does that turn from orbital stretching into a planet-wide furnace that never cools down? How do you boil a solid moon without ever touching it, and keep it boiling for billions of years? The answer starts with how Io moves around Jupiter. Io orbits Jupiter in just about 1.769 Earth days, on a path that is not a perfect circle but a slightly stretched ellipse. That small stretch is enough to matter. When Io is closer in its orbit, Jupiter's gravity pulls harder. When it is farther, the pull is weaker. Every orbit, the rock inside Io gets squeezed and relaxed. Calculations show the body can flex by on the order of 100 meters, about 330 feet up and down. That is not the surface bouncing like rubber. It is the whole interior being distorted. You can think of it as a solid body tide like ocean tides on Earth, but in rock instead of water, and on the scale of an entire world. This flexing does not happen once in a while, because the orbit is only 1.769 days long. The main tidal bulges shift and move through the interior roughly twice per orbit. So in less than 4 Earth days, the rock inside Io has been bent back and forth repeatedly. The minerals resist that changing shape, they rub and deform, and that resistance shows up as heat. The key point is that the process is regular and relentless. As long as the orbit stays slightly eccentric, Jupiter's gravity acts like a giant pump, injecting mechanical energy into Io's interior every single orbit. So here is the obvious question. If tides normally act to smooth out orbits and make them more circular, why has Io not already relaxed into a safe round path where all this violent heating shuts off? This is where Europa and Ganymede step in. Io is not orbiting alone. It is locked in a 3-body orbital resonance with Europa and Ganymede, the so-called 4-to-2-to-1 resonance. For every single orbit Ganymede makes around Jupiter, Europa makes 2 and Io makes 4. That ratio means that the moons line up in repeating patterns. At certain points in their orbits, their gravity tugs on each other in a very regular way. For Io, those repeated tugs come at just the right times to keep its orbit slightly stretched, instead of letting it circularize. Without that resonance, over tens or hundreds of millions of years, tidal forces between Jupiter and Io alone would slowly drain energy from the orbit and smooth it into a near-perfect circle. In that circular case, the strength of Jupiter's pull would not vary much over each lap. The internal flexing would drop and the heat production would fall off. But the resonance constantly pumps Io's orbital eccentricity back up. Europa and Ganymede act like a gravitational crank, adding orbital energy on a schedule that prevents Io from ever really relaxing. The result is a stable but vicious setup, with Io trapped between Jupiter's huge gravity well and the precise clockwork of its sibling moons. Once you accept that the rock is being flexed like this, the next hard question is, how much power are we actually talking about? Is this just a small internal heater, or something far more extreme? When scientists run the numbers, the tidal heating inside Io comes out to roughly 100 to 200 terawatts of power. 1 terawatt is 1 trillion watts. For comparison, all of human civilization today runs on the order of a few to tens of terawatts of continuous primary power. So Io alone is dissipating at least several times, and by some counting up to hundreds of times, the total power use of our entire species inside a body smaller than our moon. To make that more concrete, you can picture thousands of large nuclear power plants worth of energy, all running at once, buried inside a single small moon with no off switch. Spread over the surface, this gives a heat flow of around 2 to 3 watts for every square meter, compared with Earth's average of about 0.08 watts per square meter. In practical terms, if you had a 1 meter by 1 meter tile on Io's surface, the internal heat coming up under that tile would be like running a small electric heater non-stop. On Earth, that same square meter would only get the equivalent of a low-power nightlight from the planet's interior. This enormous difference is why Io can keep melting rock and feeding hundreds of volcanoes, while Earth's volcanism is confined to limited zones. The gravitational work being done every orbit is simply much larger per unit area. So if a small moon can be powered like this, what does that do to our basic idea of how rocky worlds live and die over time? Did this one data point really force planetary science to change its rules? Before Io, the standard picture for small rocky bodies was straightforward. Planets and moons form hot, they slowly cool, and the smaller they are, the faster they lose that heat. Our Moon, Mars and Mercury fit that pattern pretty well. They have old, heavily cratered surfaces, with only limited volcanic activity in their recent past. The assumption was that this is the natural endpoint for most small rocky worlds. Once they radiate away their initial heat and their radioactive elements quiet down, they should freeze geologically. Io broke that assumption. It showed that size is not the only control on geological lifespan. If a world is caught in the right orbital configuration, gravitational tides can dominate its energy budget. You can start with a cold, solid object and drive it back into a molten, hyperactive state simply by forcing it to move on a slightly eccentric path around a massive planet, with the orbit continuously stirred by resonance. Io, in that sense, is a global foundry. Rock going in as solid lithosphere, heat and tidal stress turning it into magma, and volcanic activity throwing it onto the surface and even into space. This has direct consequences for how we interpret planets around other stars. We now know about many rocky exoplanets in very tight orbits, some circling their stars in less than 1 or 2 Earth days. In multi-planet systems, these worlds can be locked into resonances that constantly pump their orbits, just like Europa and Ganymede do for Io. That means tidal magma worlds are not just a science fiction idea, they are a logical outcome of the same physics we see in the Jupiter system. A hot rocky exoplanet close to its star could be experiencing tidal heating far beyond what Io feels. with dayside lava oceans and rock vapour atmospheres driven by similar processes, so the stakes are bigger than one moon. If gravity can turn a small body like Io into a 100 plus terawatt furnace for billions of years, then we need to know what that furnace looks like on the inside. How deep does the melt go? Is there a global magma layer? And how exactly does that power connect to the volcanoes we see on the surface? Those are the questions NASA's Juno spacecraft tries to answer when it dives close and uses precision gravity measurements as a kind of X-ray of Io's interior. How do you use one small spacecraft to X-ray an entire moon without drilling a single hole? You send it skimming just above the surface and you watch its speed with extreme precision. That is what NASA's Juno probe has been doing at Io. In late 2023 and early 2024, Juno flew past Io at about 1,500 kilometers above the surface, roughly 930 miles. From that height, Io's gravity tugs on the spacecraft as well as Jupiter's, speeding it up and slowing it down by tiny amounts that radio systems can detect as shifts in frequency, down to millimeters per second in velocity. Those changes sound small, but this is where precise tracking pays off. During each close pass, Juno's radio link back to Earth is monitored constantly. When the spacecraft flies over a slightly denser region inside Io, its speed increases a bit more. Over a less dense region, the pull weakens and the speed changes smaller. By stacking data from multiple flybys and knowing exactly where Juno is along its path, scientists build a detailed map of Io's gravity field. That gravity field is a fingerprint of how mass is arranged inside, how big the core is, how thick the mantle is, and whether parts of that mantle are partly molten or mostly solid. So the next step is the key one. When you turn these gravity fingerprints into a physical interior model, what does the inside of Io actually look like? When teams take the gravity data and feed them into interior models, a clear picture starts to form. Io is not a simple coldstone sphere. It has a dense metallic core, a silicate mantle around it, and that mantle is not fully solid. To match both the total gravity and the way the tides deform the moon, you need significant melt mixed into the rock, on the order of tens of % in some depth ranges. Earlier results from the Galileo mission already suggested a global or near-global layer of electrically conductive, partially molten material tens of kilometers below the surface. Juno's gravity data refine that picture. They argue against a thin, light, completely liquid ocean sitting right under the crust, and instead favour a thicker, hotter, partially molten mantle layer, where magma and crystals form a mush that can still flow over long timescales. You're not looking at a single tank of magma under one lid. You're looking at a planet-scale plumbing system. That raises a sharper question. Has this furnace been running only recently, or has Io really been like this since the early solar system? To tackle that, scientists turn from gravity to chemistry, specifically to isotopes in Io's atmosphere. Telescopes measure the ratios of different versions of sulfur and chlorine atoms in the gas. Compared to standard solar system values, Io's atmosphere is strongly enriched in the heavier isotopes. That means huge amounts of the lighter ones have been lost to space over time. When you plug those enrichments into models of outgassing and escape, you get a strong result. Io must have been volcanically active and blowing sulfur-rich gas into space for almost its entire 4.5 billion year history. It has likely lost roughly 94 to 99% of its original sulfur inventory. The simple way to do that is to keep erupting and venting gas at a high rate for billions of years, with tidal heating continuously powering the cycle. So this is not a case where Io somehow turned on recently. It has been running as a tidal engine for most of the solar system's lifetime, long enough to strip out most of one of its key volatile elements. Now add one more layer. When Juno looks at Io in infrared light with its GIRAM instrument, it does not just see random isolated hotspots blinking on and off. In some cases, multiple distant volcanoes brighten together during the same event. The huge eruption Juno saw in late 2024, covering tens of thousands of square kilometers, is a clear example of this synchronized behavior. That pattern is hard to explain if every volcano is fed by a completely separate local magma pocket. It makes more sense if there are shared reservoirs or channels deeper down that link many vents into the same larger system. The combined gravity and infrared data point toward an upper mantle that behaves like a connected network. Instead of isolated vertical pipes, you have sills, chambers and mush zones that spread sideways, so that a pressure change in one part of the system can trigger eruptions far away. That is why when one region lights up in the infrared, several others can respond almost in step. It looks less like separate volcanoes and more like different outlets on the same overpressured plumbing. At this point, you can step back and ask a broader question. If a small moon like Io can maintain a partially molten mantle and a planet-wide magma network for 4.5 billion years, what does that say about rocky planets that are bigger and closer to their stars? For exoplanets, this is a warning. Many of the rocky worlds we have found around other stars are super-Earths, with masses a few times that of our planet. In multi-planet systems, they can easily get locked into resonances that pump their orbits in the same way Europa and Ganymede pump Io. If that happens, the tidal heating in their mantles could exceed Io's already extreme levels. Surface temperatures on those planets could sit between about 1,200 and 2,000 Kelvin, hot enough to maintain lava oceans on the dayside. Their atmospheres might not be built from water and nitrogen like Earth's, but from vaporized rock, sodium, silicon monoxide, metal vapors. In that context, Io is your local training's ground. Juno's gravity passes tell you how much melt can exist in a tidally heated mantle. Geom's hotspot maps show you how a magma network vents that energy. The isotope measurements reveal how fast a world can strip away its volatile elements under continuous volcanism. Put all of that together, and you get a template you can scale up to interpret distant magma planets that you'll never resolve as more than a single point of light. The closer Juno looks, the clearer it is that Io is not just one extreme moon, it is the baseline case for an entire class of worlds. And if the interior is this hot and this connected, what does that look like right at the surface, at the single most powerful volcano of them all, the 200-kilometer wide, roughly 120-mile wide lava lake called Loki Patera? How do you get a lava lake so big that it behaves less like a volcano and more like a small tectonic system on its own? On Io, that thing has a name, Loki Patera. It is one of the brightest infrared hotspots on the moon, a huge horseshoe-shaped volcanic depression about 200 kilometers across, around 120 miles. That means you are looking at an area comparable to a small country, but instead of fields and cities, it is mostly molten basalt. When scientists track Loki in infrared light over time, they do not see a steady glow. They see it brighten and dim in cycles that last hundreds of days. The simplest explanation is that the surface is overturning again and again as new hot material rises and old cooled crust sinks. So the obvious question is, how do we actually know that this giant feature is a lava lake and not just a cluster of hotspots? What did the first detailed measurements really show? Back in the 1990s and early 2000s, NASA's Galileo spacecraft carried an instrument called NEMS, the Near-Infrared Mapping Spectrometer. When Galileo looked at Loki, NIMS measured a very large area, more than 800 square kilometers, glowing at around 500 Kelvin on average. That is over 220 degrees Celsius, or about 430 degrees Fahrenheit. On top of that broad warm background, there were smaller patches that were much hotter, consistent with very fresh, recently exposed lava. The combination is important. A single erupting vent usually gives you a sharp, very hot spot. Loki instead showed a wide region of warm material plus scattered hotter pieces, which is what you expect if the surface is a crust forming on top of a deeper pool and then breaking, exposing hotter interior lava. Thermal models that match the data use a process called crustal foundering. The idea is straightforward. Lava at the surface cools, forms a crust that is lighter at first, then gradually becomes denser as it continues to cool and crystallize. Once that crust becomes heavier than the underlying liquid, it breaks and sinks. New hot lava then wells up to fill the gap. On Loki's scale, this is not a local crack here and there. It is a systematic pattern where large sections of the lake's surface can overturn over weeks or months. That matches the observed brightening. When a big area overturns and exposes fresh lava, Loki gets very bright in infrared. As that lava cools, the brightness drops until the next overturn event. But you might wonder, Galileo's data are decades old. Is Loki still behaving like this? Or was that a one-time pattern we just happened to catch? Juno, with its Georum infrared instrument, has now gone back and checked. The answer is that Loki is still very active. Georum images show Loki as a strong infrared source with hot regions lining up along the edge of the horseshoe and around interior islands of higher ground inside the Patera. When scientists look at how reflective the surface is in different wavelengths, they see a pattern that makes sense for a lava lake. Darker areas look like fresh volcanic glass or very young crust. Brighter patches look like older, thicker crust that has cooled longer. That pattern's not random. It lines up with models where a wave of overturn, basically a front of crust sinking and new lava rising, travels across the lake at speeds of a few kilometers per day. So you get this picture. At one end of Loki, the crust starts to break and sink. Fresh hot lava floods in, the infrared brightness spikes. Over days and weeks, this overturned front marches around the horseshoe shape, replacing old crust with new, until it has swept across most of the Patera. Then things calm down, the surface cools, the brightness drops, and eventually the cycle starts again. You can think of it as a repeating reset of a gigantic lava surface. The key point is that Juno's recent data confirm that Loki has stayed in this hyperactive mode for years and likely decades, not just during Galileo's era. This raises a bigger problem for our usual way of thinking about volcanoes. On Earth, even the largest persistent lava lakes, like the ones we've seen in places such as Mount Nyiragongo or Kilauea, are only a few kilometers across at most. Loki is about 200 kilometers across, roughly 120 miles. You are dealing with an area tens of thousands of times larger than a typical terrestrial lava lake. This is not a single cone with a small crater lake on top. It is a 200-kilometer wide convecting system. To feed something like this, you probably need a broad laterally extended magma reservoir or a whole complex of reservoirs linked together, sitting in the upper mantle of Io. That is why Loki breaks the simple single volcano picture. The power that goes into it is tied to Io's tidal heating, not just to a local patch of mantle rising up. When tidal forces change the stress and pressure conditions in the interior, they can change how magma moves through that entire region. In other words, Loki is responding to global forcing, not just its own local plumbing. On Earth, magma recharge is often controlled by plate boundaries and regional stress fields that move slowly. On Io, the main driver is the rapid, repeated flexing of the whole moon by Jupiter's gravity. Loki is one of the most visible outlets of that deeper process. Once you see Loki this way, the next question is natural. If you scale this up, could it be a good analogue for the kind of magma oceans we expect on very hot exoplanets? A magma ocean planet is a rocky world whose surface is so hot that large areas, sometimes nearly the entire dayside, are molten. Over time, that molten layer cools from the top down, forming a crust. As the crust thickens, it may start to overturn with heavy material sinking and lighter, fresher melt rising, much like what we think is happening at Loki. The physics is similar. Cooling from above, heating from below, and a dense, mobile liquid beneath a brittle lid. Loki gives you a smaller, more manageable version of that problem, one you can watch change on human timescales. By tracking Loki's brightening and dimming cycles, measuring how fast the overturned fronts move, and estimating how thick the crust gets before it fails, scientists can test and tune the same thermal and mechanical models they apply to full-scale magma oceans. They can ask questions like, how long does it take for a crust of a certain thickness to become unstable? How quickly can fresh magma rise? How much heat can be dumped through these overturn events? Those same questions matter when you look at a super-Earth exoplanet with surface temperatures of 1,500 or 2,000 Kelvin. You cannot resolve that world's surface directly, but but its infrared brightness over time might show hints of large-scale overturn, just as Loki does. So Loki is not just an interesting I/O feature. It is a working laboratory for magma ocean physics, running continuously on a 200-kilometre scale. And if one lava lake can behave like this, linked to Io's internal tides, what happens when a much larger region of the moon's surface gets triggered all at once, with many hotspots flaring together in one event that dwarfs even Loki's energy output? That is exactly what Juno saw in the record-breaking super eruption of 2024 to 2025, when an area roughly 65,000 square kilometres lit up in infrared all at once. How big does an eruption have to be before it forces you to rewrite the energy scale for an entire moon? On December 27, 2024, Juno answered that for Io. During a close flyby, when the spacecraft was about 74,400 kilometres above the surface, around 46,200 miles, its Jiram infrared instrument picked up an enormous hotspot in Io's southern hemisphere. A whole region that normally glows moderately in infrared suddenly lit up like a flare, turning that part of the moon into a single massive beacon. This was not just another active spot. The brightness jump was so extreme that the team immediately realised they were seeing something record-breaking. So here's the key point. Was this just one huge volcano blowing its top, or was something much larger going on across the surface? When scientists mapped the infrared data, they found that the event covered roughly 65,000 square kilometres, about 25,000 square miles. That is an area comparable to Lake Superior and the land around it on Earth. Multiple hotspots inside that region brightened together by a factor of more than 1,000 compared to their usual output. A feature previously known as a fairly modest hotspot suddenly became one of the brightest ever seen, and several neighbouring sites also jumped into the top tier of power output. The pattern is not one central source and a bit of spillover. It is a whole cluster of separate hotspots turning on together, across distances of tens to hundreds of kilometres. The simplest way to explain that is a shared subsurface magma system being disturbed on a large scale, with pressure or melt changes travelling under the crust and triggering eruptions at multiple vents at the same time. Now the question becomes, how much power does it take to light up 65,000 square kilometres like that, and how does it compare to what we are used to on Earth? From the Jiram measurements, and using models of how hot the lava has to be to produce that radiated energy, the total power output of this event is estimated between 140 and 260 terawatts. 1 terawatt is 1 trillion watts. Human civilization currently runs on the order of a few to maybe 20 terawatts, depending on how you count all forms of primary energy. This one eruption region on Io, by itself, was outputting something like 6 times all the world's power plants at the low end, and more than 10 times at the upper estimate. Even compared to famous eruptions, it is extreme. The 1980 Mount St. Helens eruption peaked around a few tens of terawatts. This Io event goes well beyond that, and it beats previous Io records like the roughly 80 terawatt Surt eruption in 2001. So on an energy chart of explosive events, this super eruption jumps to the top. At that scale, you have to ask what this says about the inside of Io, because an outburst like this is not just a surface firework, it is the visible tip of a huge interior system. The synchronous brightening of several hotspots inside that 65,000 square kilometre region strongly suggests they are connected below the surface. One leading idea is a broad complex of magma sills and reservoirs in the crust, linked enough that a pressure change in one part propagates laterally and destabilizes other pockets. Another is that there is a melt-rich layer in the upper mantle, where magma and crystal mush extend under a wide area, and vents tap into different parts of the same connected zone. In both cases, the interior looks more like a continuous, porous magma network than a set of isolated chambers. The fact that some nearby hotspots did not respond, even though they have been active in the recent past, hints that the connections are active. Certain volcanoes share a reservoir, others do not. That level of structure has to be built into any physical model of Io's interior from now on. But there's another angle you cannot ignore. Was this just a brief flash? Or can Io hold this kind of output for a long time? Follow-up. Durham observations in early 2025 show that the region did not just snap back to normal right away. The hotspot remained active for months. The power output dropped from its peak but stayed far above the baseline, and the thermal signature showed continuing lava supply and cooling flows. Surface imaging indicates changes in the appearance of the southern hemisphere, consistent with fresh deposits and new dark flows laid down during and after the event. In other words, this was not a single instant blast, it was a long episode, with sustained high energy release and long-term modification of the terrain. That persistence matters for the big picture. If Io can maintain 100 plus terawatts of volcanic power in one region for months, on top of all its normal activity, then these super eruptions cannot be treated as rare, one-off freak events. They start to look like extreme expressions of the same tidal forcing that is always acting on the Moon. As the orbital parameters slowly evolve over time, the total tidal heating can vary, and Io's internal system responds, sometimes with ordinary eruptions, sometimes with large-scale episodes like this. What Juno happened to catch in late 2024 and early 2025 is probably one high point in a long, ongoing cycle of stress build-up and release driven by Jupiter's gravity and the resonant tugs from Europa and Ganymede. So now the tension ramps up again. You've seen a single event where a patch of Io, bigger than Lake Superior, lights up with up to 260 terawatts of power, multiple volcanoes going off together, fed by a connected magma network and staying active for months. If a moon that small can do that, what happens when you look at individual volcanoes that almost touch space with their plumes, throwing material hundreds of kilometers up, rebuilding the atmosphere every time they erupt? How far can a volcanic fountain go in Io's low gravity, and what does that mean for the entire Jupiter system around it? How tall does a volcanic eruption have to be before it stops being a volcano and starts acting like part of space? On Io, some eruptions cross that line. Volcanoes like Pella and Prometheus throw plumes between about 100 and 500 kilometers high, roughly 60 to 300 miles. If you put those eruptions on Earth, they would blast straight through the troposphere, punch through the stratosphere, and push into the region we call low Earth orbit. During the Galileo mission, one plume at Patera was actually imaged rising to around 140 kilometers, about 86 miles. That is not a side effect. That is volcanic activity directly reaching into near space above a moon's surface. So if these fountains are reaching that high, what exactly are they throwing up there? Is it anything like the ash clouds we know from Earth? On Io, the plumes are not water-rich like the geysers at Enceladus. They are dominated by sulfur dioxide gas, SO2, along with elemental sulfur and other sulfur compounds. When these gases rush out of the vent, they expand, cool, and some of them freeze out as tiny particles. Thermal and spectral data from Voyager, Galileo, and ground-based observations show that the fallout from these plumes is basically sulfur snow. It settles back onto the surface in rings and patches that can be hundreds of kilometers wide. That is why you see those coloured bullseye patterns around some volcanoes. Dark centres where fresh lava sits, surrounded by bright rings of white, yellow, and red material. The colours come from different forms of sulfur, and from varying thicknesses of sulfur dioxide frost. It is a chemical coating laid down by every big eruption. That raises a basic physics question. Why do these plumes reach such insane heights in the first place? What makes Io such a good launch pad for this material? Part of the answer is gravity. Io's surface gravity is about 1.8 meters per second squared, roughly 18% of Earth's gravity, about 0.18 g. For the same launch speed, material on Io can reach more than 5 times the height it would on Earth before falling back. Then add the energy at the vent. Temperatures at active vents can exceed 1200 Kelvin, around 930 degrees Celsius. or 1,700 degrees Fahrenheit. At those temperatures, gas can expand violently and reach exhaust speeds on the order of a kilometre per second, about 2,200 miles per hour. In a low-gravity, almost airless environment, that is enough to throw particles on ballistic paths that climb hundreds of kilometres up. Some particles and gas molecules are launched so fast and interact with Jupiter's magnetic field and radiation environment so strongly that they never come back. They get ionized, stripped of electrons, and become charged particles moving in the combined gravity and magnetic fields of Jupiter and Io. At that point, they are no longer doing simple ballistics, they are joining a completely different system. So what happens to the material that escapes? Does it just vanish into space, or does it form something bigger that surrounds Jupiter itself? A fraction of the gas and ions from Io's eruptions get trapped in a huge, donut-shaped ring of plasma around Jupiter, called the Io plasma torus. It sits roughly at Io's orbital distance and wraps all the way around the planet. This torus is full of electrons plus ions of sulfur and oxygen that originally came from Io's volcanic gases. The densities are high for a magnetospheric plasma, thousands of particles per cubic centimetre in some regions, and the whole structure glows in ultraviolet light. As Jupiter's strong magnetic field sweeps around, it drags this plasma with it, and huge electric currents flow along the magnetic field lines, in and out of the torus and Jupiter's polar regions. We are talking about millions of amperes of current. Those currents help power parts of Jupiter's auroras, including the distinct Io footprint hotspot in Jupiter's atmosphere. So every time a major plume erupts on Io, it is not just changing the surface. It is also feeding this plasma ring and adjusting the electrical environment of the whole Jupiter system. With eruptions reaching space and feeding a plasma torus, what does that mean right back at the surface for something as basic as the atmosphere around you if you were standing on Io? The key point is that Io's atmosphere is extremely thin. Surface pressures are in the range of about 0.033 to 0.3 millipascal, that is 0.33 to 3 nanobar, around 100 million times thinner than sea level air on Earth. In that regime, the concept of weather, like we have here, almost breaks down. There is not a thick, stable blanket of air. Instead, you have a fragile layer of sulfur dioxide gas that exists because it is constantly being replenished. In sunlight, SO2, frost on the ground, warms up and sublimates, turning straight from solid to gas and building a thin atmosphere over the day side. At night, that same gas cools, refreezes, and collapses back onto the surface. On top of that day-night cycle, every big volcanic plume injects thousands of kilograms of SO2 per second directly into the atmosphere. So when a major volcano like Pelly goes off, that plume is not weather moving inside a pre-existing atmosphere. It is the atmosphere being rebuilt from the ground up in real time. Gas freezes, sublimates, erupts, some escapes to the plasma torus, some falls back as frost and sulfur snow, and the loop continues. Each eruption is a direct mechanical and chemical reset of the local air. That leads straight into the next problem. If the atmosphere is that thin and that dependent on sunlight and eruptions, how does it behave over a full Io day? What happens on the night side? And how fast can it flip between on and off as the moon moves in and out of Jupiter's shadow? Those questions push us into the next part of the story, where Io's atmosphere does something almost no other world does. It switches state on a daily basis, like a global light you can turn on and off with gravity and sunlight. How do you even call something an atmosphere when it's closer to a lab vacuum than to air? On Io, the air is mostly sulfur dioxide gas, SO2, with traces of sulfur monoxide, sodium chloride, and a bit of oxygen mixed in. Right at the surface, the pressure sits between about 0.033 and 0.3 millipascal. That's 0.3 to 3 nanobar. In simple terms, that's around 100 million times thinner than sea level air on Earth. If you could stand there in a suit and stick your hand out, you would not feel any wind on your skin. By human standards, It's basically vacuum with a little chemistry added on top. So if it's that thin, why do we even care about this atmosphere? Does it actually do anything interesting, or is it just a faint gas layer we can ignore? The way it switches on and off is exactly why it matters. On the day side, sunlight hits the surface and warms up the frozen SO2 frost that coats much of the ground. That frost sublimates, going straight from solid to gas, and that gas builds the thin, daytime atmosphere. On the night side, where there is no sunlight, the surface gets cold. The gas cools, loses energy, and refreezes back onto the ground as frost. Models show that the pressure can change by factors of around 10,000 between day and night. So as Io rotates, you're dealing with a world where the atmosphere literally condenses onto the surface every night and then reappears every day. And it doesn't just stop at thicker on the day, thinner on the night. There's a direct flow that connects them. Because the day side is constantly producing SO2 gas, and the night side is constantly removing it by freezing it out, there is a huge pressure difference between the two hemispheres. Gas naturally flows from high pressure to low pressure, so SO2 streams from the warm day hemisphere toward the cold night hemisphere. In Io's case, that flow is fast. In this ultra-thin gas, the speed of sound is lower than in Earth's atmosphere, and the flow speeds can reach hundreds of meters per second. That is fast enough to be supersonic in that environment. Early NASA models from the 1980s already predicted strong day-to-night winds, and more recent observations of spectral lines from the gas back up the idea. You have supersonic SO2 winds sweeping from the sunlit side to the dark side as Io rotates. So you've got this on-off atmosphere and these extreme winds. But remember, Io is also covered in volcanoes. What happens when one of those big plumes erupts into such a fragile gas layer? Near active volcanoes, the atmosphere gets a serious boost. The continuous output of SO2 and other gases from a strong plume can push the local pressure up to between about 0.5 and 4 millipascal, that's 5 to 40 nanobar. That's still tiny compared to Earth, but it's thousands of times denser than the average background on Io. Around a major hotspot, you suddenly have a thicker pocket of gas with its own flow patterns. Plume gas shooting up and falling back collides with the surrounding thinner atmosphere. That creates shocks, local winds, and complex circulation where the eruption effectively makes its own mini-weather system. On top of that, Jupiter's magnetosphere is constantly dumping charged particles and ultraviolet radiation into this gas. Those inputs drive chemical reactions, breaking SO2 apart, forming sulfur chains, oxygen, and a mix of ions. So around a big volcano, you not only get thicker gas, you get a local chemistry lab being powered by both tidal heat from below and charged particles from above. It's a crossover zone where geophysics, atmospheric physics, and plasma physics all run at once. When you zoom out, the rhythm of this whole system is not slow. On Earth, large-scale atmospheric cycles like changes in circulation patterns or shifts in climate play out over months, years, or longer. On Io, the entire atmosphere flips state every single Io day, roughly every 1.77 Earth days. Sunlight turns frost into gas, rotation carries that gas into shadow, cold turns it back into frost, volcanoes punch holes and add new gas, and plasma from Jupiter strips some of it away and lights it up. It is a climate system running in fast forward, with cycles tied directly to the orbit and to the pulse of volcanic activity, not just to slow seasonal changes. For people who model atmospheres and climates, Io is basically a stress test. You have a world where gas, frost, and plasma interact on timescales of hours to days, not centuries. You can't treat the surface as a fixed boundary, or the atmosphere as a slow, smooth layer. Everything is responsive and coupled, and that leads to the next tension point in the story. If the atmosphere is flipping this fast, and the surface is constantly getting buried and resurfaced, what does that do to the solid crust itself? How do you end up with mountains taller than Everest on a world that has no plate tectonics, and yet is being crushed, pulled, and resurfaced at insane rates? How do you get mountains taller than Everest on a small moon that doesn't even have plate tectonics? On Io, That's exactly what you see. The surface is not just flat lava plains and volcanic pits. High-resolution images and topography show isolated mountains rising up to around 17 kilometers high, over 55,000 feet, from base to peak. That's almost twice the height of Mount Everest if you measure from the foot of the slope, not sea level. These are huge, freestanding blocks, often with steep, sharp cliffs. And yet, there are no Earth-style tectonic plates here, no subduction zones, no continents colliding. So if the crust is not doing plate tectonics, what is pushing these blocks up? Start with how the surface is being treated over time. Io is constantly resurfaced by lava flows and plume deposits. Fresh material comes up, spreads out, cools, and becomes part of the crust. If you keep adding new material on top, and you do it globally for millions and billions of years, the outer shell gets squeezed. It has nowhere easier to go. On Earth, moving plates can slide and dive under each other, releasing that horizontal stress. On Io, the lithosphere behaves more like one continuous lid. When it is forced to accommodate all that fresh lava, it goes into compression. The leading idea is that this compression doesn't stay smooth. The crust breaks into big blocks along deep faults. Some of those blocks get thrust upward and tilted, forming massive isolated peaks with steep scarps on one or more sides. You can picture a big slab of crust being pushed up and rotated, so one face becomes a near vertical wall and the top becomes a high plateau. These fault blocks can reach tens of kilometers in height and stretch for hundreds of kilometers in length. They are not built by slow stacking of volcanic layers like a shield volcano. They are built by mechanical failure of a crust that is being squeezed from all sides. Now think about what volcanism is doing at the same time. Volcanism thins and weakens the crust. Every time magma rises and erupts, it removes material from depth and replaces it with fresh, hot rock closer to the surface. That tends to lower the effective strength of the crust, make it easier to deform, and in many places simply flood everything with lava and erase topography. Compression, on the other hand, wants to thicken the crust and push parts of it upward. So across Io you have a constant tug of war. Where compression wins over local melting and collapse, you build mountains. Where volcanism wins, you get broad calderas and smooth plains. The result is a patchwork landscape. You can have a 15-kilometer high block with huge cliffs on one side, sitting right next to a low fresh lava field only a few hundred meters thick. Some mountains show signs of later modification, with landslides cutting into their flanks and small lava flows pooling at their bases. But the basic structure is that of massive, uplifted slabs. This mix tells you something important. Io is not just a flat lava world. Its crust has enough strength and thickness, at least in some regions, to fail in a brittle way and hold up enormous topography against its own gravity. Remember, gravity on Io is only about 0.18 g, so rock can support steeper slopes and higher cliffs than on Earth before it collapses. That lower gravity helps these mountains stand as extreme freestanding structures rather than crumbling into lower hills. But that alone doesn't explain where they show up. For that, you have to look at how stresses are distributed across the whole moon. If tidal heating were the only driver, you might expect a clean pattern. Simple models of tidal heating inside Io predict that the strongest heating happens either near the poles or in specific latitude bands depending on exactly where the energy is being dissipated inside. If you then assume that hotter regions are weaker and more prone to volcanism, and cooler regions are stronger and more prone to compression and uplift, you'd predict that mountains should cluster in certain cold zones where the crust is thicker and stronger. But when you actually map where the big mountains are, the pattern does not line up neatly with those simple predictions. Many of the tallest mountains do not sit in the expected cold spots. Instead, a lot of them cluster near the equator, or in longitudes that do not obviously match the peaks and troughs in the basic tidal heating maps. Some areas that tidal models say should be hot and weak still host giant mountains. Other zones that look ideal for uplift are oddly quiet. That mismatch is a major clue. It tells you that our first order view of heating map equals stress map equals mountain map is incomplete. Something inside Io is redistributing stress in a more complex way. It could be that heat is not deposited evenly with depth, so some regions get strong, focused heating in the shallow mantle while others get it deeper down. It could be that the crust has a big variations in thickness and composition, maybe due to long-term patterns in volcanism, so some areas resist deformation more than others. It could also be that mantle convection patterns, basically slow, large-scale flow inside, are shifting where compression and extension take place over time. Whatever the details, the key point is that these 17-kilometre-high mountains are not just random features. They are physical records of how Io's crust has been squeezed, broken, and stacked over geologic time. Each peak is a marker of where compression beat volcanism strongly enough for long enough to punch a block of crust up and hold it there. Together they form a kind of stress map, highlighting where the lithosphere has absorbed the tidal forcing and where it has given way. And there's another angle you can't ignore. Those towering mountains are sitting in a landscape coated with sulfur dioxide frost, and ultra-hot silicate lavas. Their slopes get painted and repainted by plume fallout, lava splashes, and chemical reactions driven by sunlight and radiation. If you zoom out from individual peaks and look at the whole moon, the first thing you notice is not the mountains themselves, but the colours. Yellows, oranges, reds, blacks, whites, scattered all over. So the next question is simple and direct. If the crust is being ripped, uplifted, and resurfaced like this, what exactly is all that stuff on top? And what do those intense colours tell you about the temperatures and chemistry of Io's eruptions? Why does Io look like someone dropped a chemistry lab on a pizza and then turned up the heat? When you look at it in true and enhanced colour, you see yellows, oranges, reds, greens, white patches, and black lava plains all jammed together. Spectral measurements from the Voyager and Galileo missions, plus Hubble and big ground-based telescopes, all tell the same story. The surface is coated with sulfur dioxide frost, and silicate lavas that are mostly basalt. The different colours come from different forms of sulfur, called sulfur allotropes, and from how thick the sulfur dioxide frost layer is in each spot. So when you see a bright white or grey area, you're mostly seeing SO2 frost. Yellow and yellow-green regions are dominated by sulfur deposits. Red and brown tones often show up where sulfur has been battered by radiation or mixed with other compounds. The result is that every patch of colour is basically a composition code. Dark, low albedo areas tend to be fresh silicate lava or older basaltic plains. Bright rings around volcanoes tell you where plume fallout has landed. To a planetary geologist, Io's toxic pizza look isn't just weird, it's data stamped directly onto the surface. But colours alone don't tell you how extreme the lava is. The real shock comes when you look at the temperatures. Thermal emission from active lava flows and hotspots on Io shows brightness temperatures of at least about 1,200 Kelvin, and in some cases probably up to around 1,600 Kelvin. That's roughly 930 to 1,330 degrees Celsius, or about 1,700 to 2,400 degrees Fahrenheit. Those numbers are much hotter than most modern basalt flows on Earth. On Earth, you usually see basalt erupting at around 1,100 to 1,250 degrees Celsius. On Io, some hotspots like the famous Pale region match temperatures you'd expect from very magnesium-rich ultramafic lavas, similar to the komatiites that erupted on early Earth billions of years ago. So in simple terms, you're not just dealing with regular basalt. You're looking at extremely hot, low-viscosity magma that can flow fast and stay molten over long distances. That fits perfectly with the idea of a mantle that's strongly heated by tides, where parts of it are partially molten on a global scale. The lava temperatures are a direct hint that the interior of Io is tapped into a very hot, very efficient melt source. Then you flip to the coldest side of the story and it gets even stranger. Those bright snowfields you see around many volcanoes aren't water ice. They're frozen sulfur dioxide, sometimes mixed with other sulfur compounds. In many of these regions, surface temperatures can drop below about 130 Kelvin, which is around minus 143 degrees Celsius or minus 225 degrees Fahrenheit. At those temperatures, SO2 collapses out of the gas phase and sticks to the ground as frost or ice. Measurements and models show that large portions of Io's surface, especially in white or grey areas, are covered by this frost, stable in the cold and ready to sublimate again when sunlight hits. So in one place you can have lava hotter than almost anything erupting on modern Earth, and not far away you can have a frost layer sitting at temperatures that are colder than almost anywhere on our planet. The rock gas that erupted from the interior literally snows back onto the surface and becomes part of the next day's atmosphere. Now the next logical question is, with lavas this hot and frost this cold, how fast does the surface actually change? Is this just a frozen pattern, or is the paint job moving on human timescales? Comparing images from Voyager in the late 1970s with those from Galileo in the 1990s, and then from newer ground-based and space-based observations, scientists have seen clear changes. During the 5 years of the Galileo mission alone, careful surveys found more than 80 surface changes, new dark lava flows, fresh plume deposits, and noticeable shifts in colour and brightness around many volcanoes. Some areas that were once bright with sulphur frost got darkened by new flows. Others gained new white and red rings from plume fallout. On longer timescales, the global colour pattern is surprisingly stable in broad outline, but locally it's very active. Big regions can shift from bright to dark and back over just a few years. When you see a dark fresh flow on Io, that is not ancient history. That is recent or ongoing volcanism repainting the ground. Its albedo map, the brightness pattern, is not a static map like our moon's. It's closer to a time-lapse that updates every time a major eruption happens. This is where the chemistry and the colours become more than just pretty pictures. They're tools. By tracking which colours appear where and watching how they change with time, researchers connect them to lab measurements of sulphur allotropes and silicate minerals. Different forms of sulphur absorb and reflect light in different ways. Some turn from one colour to another when you heat them above certain temperatures or expose them to radiation. Basaltic and ultramafic lavas have characteristic spectral signatures as well, so you can do something powerful. You see a flow go from very dark to a slightly lighter tone over a known time interval. That lets you estimate cooling rates. You see a red ring fade and shift toward yellow or white that hints at how fast certain sulphur species are transforming or getting buried. You see fresh black flows appear exactly where high-temperature hotspots were detected before, that ties temperature, magma composition, and eruption style together. In effect, you're reading Io's eruption history using layers of coloured sulphur and glass instead of layers of ice or rock cores. For planetary science, this is extremely useful when you look outward. A lot of the exoplanets we find, especially the very hot rocky ones, are never going to be resolved as disks. You will only get changes in brightness and colour over time. Io shows you how a highly active volcanic surface with sulphur and silicate materials can evolve rapidly and still keep a recognisable large-scale pattern. It teaches you what chemical chaos looks like when it's driven by tidal heating, plasma bombardment and extreme volcanism. And that rolls directly into the next step in the chain. All that sulphur, glass and lava is not just sitting there looking weird. It is plugged into the electrical and magnetic environment of the whole Jupiter system. The same volcanoes that paint the surface also inject gas and plasma that drive electric currents and light up auroras on Jupiter itself. So the next question is sharp and unavoidable. If Io's surface is this violently active, what happens when you connect it to Jupiter's magnetic field? How does one small moon end up acting like a generator that helps power giant auroras on a gas giant? How does a small moon end up acting like part of a power plant for a giant planet? With Io, the same volcanoes that spray gas into space also help drive electric currents and auroras on Jupiter, and the link is very direct. Start with the basic setup. Io orbits deep inside Jupiter's huge magnetic field. Jupiter's magnetic field and plasma environment rotate almost with the planet's 10-hour day, much faster than Io's 1.77-day orbit. That means the magnetic field lines and the surrounding plasma are effectively sweeping past Io at high speed. Io itself, plus the cloud of ionized gas around it, is electrically conductive. Put a conductor moving through a magnetic field and you've made a generator. Because of that motion, a voltage is induced across Io, with one side at a higher electric potential than the other. That drives currents along the magnetic field lines that thread the Moon and connect it to Jupiter's upper atmosphere. The numbers are not small. Estimates put the current in this Io Jupiter flux tube at around 3 to 5 million amperes. A strong lightning stroke on Earth is maybe 30,000 amps, so this one circuit carries on the order of 100 times more current than a big lightning bolt continuously, not just for a split second. It's like having a live wire stretched across space from Io down into Jupiter's atmosphere. So what does all that current actually run? Is it just flowing pointlessly, or does it power something visible? A big part of the answer lies in the plasma torus around Jupiter. Volcanic plumes on Io throw out huge amounts of sulfur dioxide and other gases. Some of that material never falls back. It gets ionized by solar ultraviolet light and by collisions with energetic particles and electrons in Jupiter's magnetosphere. Once ionized, the sulfur and oxygen atoms are picked up by the rotating magnetic field and trapped, forming a thick ring of plasma centered roughly on Io's orbit. This is the Io plasma torus. Densities in the torus reach thousands of particles per cubic centimetre near the torus core, which is very dense for a planetary magnetosphere. That plasma emits strongly in ultraviolet and visible wavelengths as the electrons collide with ions and excite them. Spacecraft like Voyager, Galileo and Juno, and telescopes from Earth, have all measured these emissions. The torus is effectively a big reservoir of mass and charge that Jupiter's rotating magnetic field has to drag around, and that drag is tied to the electric currents flowing through the system. Now connect that back down to Jupiter's poles. Where does the flux tube current actually go? The magnetic field lines that thread Io and its plasma environment are rooted in Jupiter's upper atmosphere at high latitudes. The current that flows along those lines dumps energy into the upper atmosphere where the field lines hit, accelerating electrons and heating the gas there. That produces localized auroras, bright spots in Jupiter's polar lights called the Io footprint. Telescopes like Hubble and large ground-based observatories see this as a bright patch plus trailing arcs in Jupiter's auroral oval. As Io orbits Jupiter, the footprint moves around the pole, and the brightness of the spot changes depending on how much material is coming from Io and how strong the currents are at that time. So when you see that bright Io footprint glowing in Jupiter's aurora, you are looking at a direct, visible signature of electromagnetic coupling across hundreds of thousands of kilometers. Interior heat on Io drives volcanism. Volcanism feeds plasma. Plasma changes the current, and the current lights up Jupiter's poles. This forces you to connect fields that are usually treated separately. In a typical solar system course, volcanoes are geology, and auroras are space physics. On Io, they are literally two ends of the same circuit. If volcanic activity on Io ramps up, more sulfur and oxygen get blasted into space. That increases the density of the plasma torus. A denser torus changes how easily Jupiter's magnetic field can drag the plasma around, which changes the electric fields and currents needed to keep everything moving. Stronger currents then can lead to a brighter Io footprint in Jupiter's aurora, and more intense energy deposition at the poles. If activity on Io drops, the torus mass loading can decrease over time, currents adjust, and the auroral signature responds. You can think about it step by step in a very straightforward chain. Tidal heating inside Io powers extreme volcanism. Volcanism injects SO2 and other gases into space. Those gases are ionized and become part of the Io plasma torus. The rotating magnetic field of Jupiter interacts with that torus, driving currents along the field lines. Those currents hit Jupiter's atmosphere and generate auroral hotspots, including the Io footprint. Change one link in that chain and the whole system responds. That's why scientists now treat Io, the torus, and Jupiter's auroras as one coupled system rather than three separate problems. And this coupling raises the stakes again. If one small moon can push mass into a magnetosphere, drive million-amp currents, and modulate a gas giant's auroras, what does that say about the long-term evolution of Io's own surface and crust? Because the same process that powers all this, tidal heating, also tries to raise Io's past as fast as it can write it. That brings us to the next question. On a world this active, where almost everything is getting resurfaced, how much of its history can the surface actually remember? And where do we look for the long-term record? How do you tell the age of a world that keeps deleting its own surface? One of the first big shocks from the Voyager images of Io was how clean it looked. On a solid body that's been around for about 4.5 billion years, you expect a surface like our Moon or Mercury, packed with impact craters of all sizes. Instead, Io looked almost smooth at Voyager's resolution, with bright and dark patches, volcanoes, lava flows, but very few obvious craters. That's the first hard clue. The surface cannot be old. The only way to wipe out craters across a whole moon is to keep resurfacing it, and do it fast enough that impacts never get a chance to build up a visible record. When people ran the numbers, the picture got even more extreme. To keep crater density that low over billions of years, you need global resurfacing rates on the order of centimeters per year, not millimeters per 1,000 years. That sounds small, but remember, that's averaged over the entire surface. Lava flows spreading out from vents, plus sulfur and sulfur dioxide snow falling out of plumes, add up. Over 1 million years, centimeters per year becomes tens of meters of new material. That is more than enough to bury most craters, especially the smaller ones that dominate the statistics. So when you look at Io today, you're not seeing a long, layered impact history. You're mostly seeing the last slice of time, the most recent flows, the latest plume deposits, the fresh lava lakes. To see how extreme that is, it helps to compare it straight to Earth. On Earth, yes, we have active volcanism, but the average volcanic resurfacing rate is tiny when you spread it over the whole planet. Most crust gets recycled at plate boundaries over tens to hundreds of millions of years. A patch of ocean floor might last 100 to 200 million years before it gets subducted. The continents keep some older rocks at the surface, billions of years old in places. If you pick a square kilometre on Earth at random, the odds are high that it has not been directly covered by fresh lava or ash in the last few million years. On Io, that same square kilometre is in a totally different regime. Lava flows, plume fallout, and collapsed structures can cover and recover the area in thousands to hundreds of thousands of years. Per square metre, Io is out-erupting Earth by at least an order of magnitude. The tidal heating is strong enough that volcanism is not a background process. It is the main agent shaping the surface. That's why impact craters are rare. They arrive at some random time, leave a mark, and then the mark gets buried, melted, or blasted apart by the next few rounds of lava and plume deposits. This has a big consequence for how you read the geology. On our moon or on Mars, you can look at overlapping craters, count them, and infer the age of surfaces. You can see ancient basins, half destroyed by later impacts, still recognizable. On Io, that kind of long surface memory barely exists. The crust is probably layered in a complex way, with older terrains buried under tens or hundreds of meters of younger basalt and sulfur. But from orbit, you mostly see the last geologic heartbeat. Volcanoes, calderas, mountains, and plains that reflect the current and recent stress and heat pattern, not necessarily the deep past. So you end up with a paradox. Io is one of the richest worlds in terms of active processes, but one of the poorest if you're trying to find direct surface fossils of its earliest history. If you want to know how long this hypervolcanic state has been going on, the rocks you can see aren't very helpful. They're too young, too frequently recycled. That pushes you to look somewhere else for the long timescale record. Here's where the atmosphere becomes important in a way that isn't obvious at first. The gases Io is throwing out are not just disappearing unnoticed. Over billions of years, they leave a chemical fingerprint. When we measure the ratios of different sulfur isotopes in Io's atmosphere, lighter versus heavier versions of sulfur atoms, we see a strong enrichment in the heavier isotopes compared to the baseline values you'd expect from the early solar system. The simplest way to get that pattern is to keep outgassing sulfur, let some fraction of it escape to space, and recycle the rest over and over for a very long time. Lighter isotopes tend to be lost more easily in many escape and fractionation processes, so after billions of years of continuous volcanic release and partial escape, the remaining sulfur reservoir ends up skewed toward heavier isotopes. When you plug that into models of outgassing and atmospheric escape, the results point to something important. Io has likely been in a high-output volcanic mode for most of its existence, not just for a short recent phase. The atmosphere, thin as it is, behaves like an integrated log of all the sulfur that has been processed through Io's volcanoes and then partly stripped away by space. So you get this split picture. The surface is short-term memory, constantly rewritten, mostly telling you what tidal heating and stress look like right now and in the recent past. The atmosphere is long-term memory, encoding billions of years of volcanic cycling in its isotopes. To really understand how long Io has been this intense, you cannot just stare at the lava flows and mountains. You have to read the gases too. And that leads to a bigger comparative question. If Io can erase its craters, bury its past, and still carry a deep history in its chemistry, how does that compare to other rocky worlds like Earth and Venus, which have different heat sources and different resurfacing styles? In other words, if you line up Io, Earth, and Venus side by side, you get 3 ways to run a magma planet. The next step is to put them in the same frame and see what that tells you about how rocky worlds handle internal heat and surface renewal. How do 3 rocky worlds built from almost the same basic stuff end up living completely different geological lives? Line up Io, Earth, and Venus. All 3 are silicate rocks with iron-rich cores. All 3 have, or had, intense volcanism, but the engines running them are not the same, and that changes everything about how they move heat, build surfaces, and link their interiors to their skies. Start with the power sources. Io is dominated by tidal heating. Jupiter and the orbital resonance with Europa and Ganymede constantly flex it, turning orbital energy into internal heat. Earth is mainly powered by radioactive decay in the mantle and core plus leftover formation heat, and it gets rid of that heat through plate tectonics and mantle plumes. Venus is similar in composition to Earth, and its main heat source is also internal radioactivity and primordial heat, but it does not show clear plate tectonics. Instead, it probably cools through what's called stagnant lid convection. The whole outer shell behaves as one big lid, with hot plumes punching through here and there. Now look at the numbers for how much heat each world actually pushes out. For Io, estimates of global heat flow cluster around 2 to 3 watts per square meter. Earth averages about 0.08 watts per square meter. Venus seems to be in between, probably a bit higher than Earth, but nowhere near Io levels. In practical human terms, if you covered a 1 meter by 1 meter patch of Io's surface with a perfect heat collector, you'd get the equivalent of running roughly a 200-watt space heater for every square meter of your apartment floor. On Earth, that same square meter gets more like the output of a single small decorative light bulb from the interior. That difference in heat density is why Io melts rock almost everywhere and constantly. While Earth only melts rock in narrow zones like mid-ocean ridges, subduction zones and hotspot tracks, heat engine first, surface style second. What does each world actually build with that energy? On Earth, plate tectonics breaks the surface into moving plates. You get continents, ocean basins, mid-ocean ridges, deep trenches, mountain belts like the Himalayas, and volcanic arcs. The crust is recycled over tens to hundreds of millions of years. Some rocks survive from early Earth, but a lot of the surface is relatively young in geologic terms, reshaped by plate motions and erosion. Venus plays a different game, There are no clear plate boundaries like our mid-ocean ridges or subduction zones. Instead, radar images show huge basaltic plains, massive shield volcanoes, and strange circular or oval structures called coronae, where the crust has been pushed up and deformed by underlying mantle flow. There's evidence that Venus may undergo episodes of more global resurfacing, where large fractions of the surface are flooded by lava over relatively short geologic timescales, then things quiet down again. Io is another step away. It has no oceans, no continents, no plate network, and almost no impact crater record. Its surface is dominated by lava flows, volcanic pits called Planetary, and isolated giant mountains that are fault blocks pushed up by crustal compression. Lava plains cover vast areas, Planetary mark caldera-like collapse structures, and plume deposits paint bright rings around vents. If you ask, what happens if you increase the heat, turn off plates and add intense tidal flexing? Io is that experiment already running. Its surface is what you get when volcanism is not one process among many, but the central player. You also see 3 different kinds of top-down control from the atmosphere. On Earth, the atmosphere and oceans interact with the interior through the water and carbon dioxide cycles. Water lowers the melting point of rocks and lubricates plate boundaries. Subduction drags water and carbonates down. Volcanism vents them back up. CO2 in the air helps set climate, which affects erosion rates and even how sediments are deposited and later subducted. The interior and the atmosphere are in a long, slow feedback loop. On Venus, the atmosphere is extremely thick, mostly carbon dioxide, with a surface pressure about 92 times Earth's and temperatures around 735 Kelvin, roughly 460 degrees Celsius or 860 degrees Fahrenheit. That massive greenhouse blanket traps internal heat and changes how the planet loses energy. A hot surface and insulating atmosphere may slow the cooling of the interior and influence mantle convection patterns. Some models suggest that this could encourage episodic catastrophic resurfacing instead of constant plate-style recycling. On Io, the atmosphere behaves very differently. It is thin, switching on and off between day and night, and made mostly of sulfur dioxide. It does not drive climate in the way Earth's or Venus's does. Instead, it acts more like a live readout from the interior. When volcanic activity increases, more SO2 is pumped into the gas phase. When activity drops or regions fall into shadow, SO2 freezes out onto the surface. The state of the atmosphere at any given time tells you directly how much gas is being emitted and where. There is still feedback. Plume gas affects plasma interactions, which can affect surface chemistry, but the chain is shorter and more direct. Interior heat to volcanism to gas to thin, fast-changing atmosphere. If you put all that together, you get 3 distinct feedback loops between mantle and sky. On Earth, internal heat drives plate tectonics and volcanism. Volcanism plus biology and weathering sets CO2 and water content in the atmosphere and oceans. Climate feeds back into erosion and sedimentation, which alters subduction input and long-term mantle composition and behavior. On Venus, internal heat drives plume volcanism and possibly episodic resurfacing. Volcanism maintains a thick CO2 atmosphere. That atmosphere traps heat, sets extreme surface temperature, and influences how the mantle convects and cools back down. On Io, tidal heating drives extreme volcanism. Volcanism vents sulfur and SO2. Those gases build a thin, rapidly changing atmosphere and feed the plasma torus. Plasma interactions and radiation alter the surface and atmosphere chemistry, but do not significantly insulate the interior. The atmosphere mainly reflects what the interior is doing, rather than strongly controlling it. Seeing these 3 side by side makes one thing very clear. Rocky worlds with broadly similar ingredients can end up in completely different regimes just by changing how they are heated and how they lose that heat. Add strong tides like on Io, and you move into continuous global volcanism. Add thick CO2 and no plates, like on Venus, and you likely get super greenhouse conditions and episodic resurfacing. Keep plates and a moderate greenhouse like on Earth, and you get a more balanced, long-lived system with oceans and continents. The next step is to ask the obvious and more troubling question. If just these three local examples are so different, what happens when you go out to exoplanet systems packed tight around their stars? There you can combine Io-level tidal heating with Venus-level irradiation and maybe Earth-like bulk composition. Do you end up with planets that are basically giant versions of Io, with whole hemispheres turned into magma oceans and rock vapor atmospheres? That is where Io stops being just a weird moon and becomes a blueprint for worlds we're only starting to detect. How do you study worlds that are basically oceans of molten rock when you can't get anywhere near them? That's where Io comes in. We've now found rocky exoplanets that orbit their stars in less than a day, with estimated dayside temperatures over 2000 Kelvin, hotter than many blast furnaces. At those temperatures, the dayside is probably molten, and the air is made of rock vapor, not water. We will never land there with current technology, but right here, with Io, you have a smaller, tidally heated magma world running the same basic physics at a more manageable scale. So the first question is simple. If the ingredients and temperatures are so different, why is Io still a good analogue for these ultra-hot super-Earths? Io gives you the full chain in one place. Inside, tidal heating keeps a partially molten mantle and large magma reservoirs active. At the surface, you have extremely hot silicate lavas, 1200 to 1600 Kelvin in some hot spots, plus a thin atmosphere built from rock-derived gas, mostly sulfur dioxide. Above that, you have intense UV radiation from the sun and charged particles from Jupiter's magnetosphere constantly bombarding that gas. The result is an atmosphere that freezes out, sublimates, gets chemically processed, and partly escapes to space. That is exactly the kind of feedback you expect on a close-in magma exoplanet, just with different dominant elements. On Io, the main volatile is sulfur. On an ultra-hot super-Earth, the main vapors would be sodium, silicon monoxide, magnesium, iron, and other rock species. But the toolkit you use to model them, radiative transfer, photochemistry under strong UV, gas flow, and atmospheric escape is the same. The same equations that describe SO2, freezing and boiling on Io, get reused with different molecules for rock vapor atmospheres. Observations of planets like TOI 561b, where web data suggest a thick atmosphere over a global magma ocean, are being interpreted with exactly these kinds of models. Next, think about how we even detect these exoplanets. We don't see continents or lava lakes directly. We see light curves and spectra. One key tool is the phase curve, how the planet's infrared brightness rises and falls as it orbits its star and shows us different faces. On a simple, evenly heated ball, the phase curve is smooth. The brightest point lines up with the day side facing us, the dimmest with the night side. But if the surface has patchy hotspots, lava lakes, giant fresh flows, regions of cooler crust, the pattern gets more complicated. Io is basically a nearby example of that. Its infrared emission is not uniform. Loki Patera, Pele, and other hotspots flare and fade on timescales of days to months. Juno and ground-based telescopes see big swings in total thermal output when something like the 2024 to 2025 super eruption lights up tens of thousands of square kilometers at once. If you wrapped Io around a star and watched it as a distant point, you would see a phase curve with bumps and irregularities as different volcanic regions rotate in and out of view and change brightness. That's a direct lesson for ultra-hot super-Earths. If one of those planets has global magma oceans plus a few Loki-scale bright spots, its phase curve could look very different from a smooth black body. You might see hot regions shifted east or west of the substellar point, or time-variable brightness as lava lakes overturn. When observers see weird offsets and variability in real exoplanet phase curves, Io gives them concrete physical scenarios to test. There's also a deeper mindset shift here. Before Voyager flew past Jupiter, the default assumption was that small rocky moons were geologically dead. No one was expecting the most volcanic body in the solar system to be a little moon. Io demolished that idea. It showed that with the right orbital setup, gravity alone can keep a rocky body molten and hyperactive for billions of years. Now look at modern exoplanet catalogues. We see plenty of 1.3 to 1.8 Earth radius planets jammed close to their stars, some in multi-planet systems with clear resonances. Theory already says they're likely tidally locked, with permanent day sides that are hot enough to melt rock. Webb is now starting to show evidence that at least some of them, like TOI 561b, really do have thick atmospheres sitting over global magma oceans. Once you put those pieces together, the Io lesson becomes hard to ignore. If a small moon in our own system can maintain hundreds of terawatts of tidal heat, a partially molten mantle, and constant resurfacing, then a larger rocky exoplanet under stronger stellar and tidal forcing is almost guaranteed to be more extreme, not less. Instead of asking, could any rocky planet out there be like Io, you flip the question. For many close-in super-Earths, the default expectation is that they are magma worlds, unless something has stripped their atmospheres, removed their volatiles, or changed their orbits enough to shut the tides down. So Io ends up as your calibration point. It tells you how hot silicate lavas can get under tidal heating, how fast you can resurface a world, how an atmosphere built from rock-derived gas behaves when it's constantly frozen out and re-released, and how patchy hotspots distort a planet's thermal signal. Then you scale up. Stronger tides, higher stellar flux, maybe more mass. The result is the family of ultra-hot super-Earths and lava planets we are now starting to glimpse. And that brings you back to a tight, unnerving conclusion. If molten rock worlds are common and Io is the nearby prototype, the next big question is why Io's own volcanoes sit where they do. Because if we can't fully predict hotspot patterns on this one, how confident can we be when we draw maps for planets we'll never resolve? That puzzle, why some regions of Io are packed with volcanoes and others are quiet, feeds directly into how we think magma is stored and moved in any tidally stressed world. Why do Io's volcanoes refuse to follow the simple maps we draw for them? When you take everything we know about its orbit, its shape, and Jupiter's gravity, you can calculate where tidal heating inside Io ought to be strongest. Depending on the exact model, you often get patterns that favour high latitudes or specific longitude belts. On paper, those are the places where you expect the most melting and, by extension, the most volcanism. But when you overlay that on the real hotspot map from Voyager, Galileo, ground-based telescopes, and now Juno, the match is not clean. Some areas the models flag as hot are relatively quiet. Some supposedly cold areas are crowded with active Patera and bright thermal sources. The real surface pattern is messy, and that mismatch is one of the big open problems. So the first question is, what could break the simple where you heat is where you erupt rule? One idea is that the heating is not uniform with depth. Tidal dissipation might be strongest in a certain layer of the mantle, not right under the crust. If most of the energy goes into a deep or mid-mantle shell, melt and heat will tend to rise in focused upwellings, mantle plumes, instead of coming up directly above the raw heating maxima. In that picture, Io becomes an extreme test case for plume theory. You have a highly stressed, partially molten mantle, with hot, buoyant regions rising, spreading sideways, and maybe feeding chains or clusters of volcanoes far from the original heating peak. On Earth, plume ideas are used to explain places like Hawaii or Iceland, where hot material rises from deep in the mantle and punches through the lithosphere away from plate boundaries. On Io, the same basic physics could be running in overdrive. Strong localized plumes might carry heat laterally under the crust before it escapes, decoupling the location of surface volcanism from the deeper dissipation map. That would naturally produce a hotspot pattern that looks offset or smeared relative to the simple tidal models. A second angle targets the crust itself. Even if the heating pattern in the mantle is relatively smooth, the crust might not be. Over billions of years of intense volcanism and compression, Io's lithosphere has been faulted, tilted, and buried multiple times. That history can leave behind weak zones, old fault plains, boundaries between thick and thin crust, sharp changes in composition, buried calderas, and ancient intrusive bodies. Magma rising from below does not just push straight up, it follows paths of least resistance. If certain longitudes or latitude bands are full of these inherited weaknesses, magma will tend to collect and erupt there, regardless of where the absolute heating maximum is at depth. In that scenario, the crust behaves like a filter. The mantle may be heated in one pattern, but the crust only lets through eruptions in certain places. Juno's gravity and topography data are starting to be good enough to test parts of this. Slight variations in the gravity field can reveal where the crust is thicker or thinner. Subtle topographic bulges and depressions can mark long wavelength flexure and loading. By correlating those structural features with hotspot locations, scientists can look for systematic links. For example, do major volcanoes cluster where the crust is thinnest, or along edges between thick and thin zones, or near big blocks that have been tilted and faulted? There is also the question of time. Tidal heating patterns can shift slowly as Io's orbit evolves and as its interior responds. At the same time, repeated volcanism can change the crust's thickness and composition, which in turn changes how stress is distributed. You don't just have a static heating map and a fixed crust. You have a feedback loop. Heat drives eruptions, eruptions modify the crust alters the stress paths, and that changes where future eruptions prefer to occur. Over millions of years, that can build up complicated, possibly migrating belts of activity. Then there's the big structural unknown, how magma is stored and connected under the surface. The 2024 to 2025 super eruption that lit up about 65,000 square kilometers at once made one thing very clear. Some volcanoes are not independent. They are plugged into a shared system. Multiple widely separated hotspots in the southern hemisphere brightened together by factors of hundreds to 1,000 and stayed unusually active for months. That kind of synchronized behavior is hard to explain if each volcano taps a small isolated magma pocket. It points toward at least regional scale reservoirs, or a continuous melt-rich layer in the upper mantle that can transmit pressure changes and trigger eruptions tens or hundreds of kilometers apart. The open question is scale. Does Io have a small number of continent-sized reservoirs feeding dozens of vents? Or a hierarchy? Local chambers linked into larger sill complexes, all sitting above a global or near-global partially molten layer? In the first case, volcanoclusters might mark the edges or centers of these big reservoirs. In the second case, the pattern might be governed more by where the crust is weakest above a broadly distributed mush. Every new Durham hotspot map from Juno adds a data point. When one region brightens, scientists check which other regions respond and which stay quiet. They track how often certain Paterae go off together, and how that correlates with Io's orbital position and the predicted tidal stress field. Over time, that builds up a kind of connectivity map. Who is talking to whom underground? Combine that with gravity-based crust thickness estimates and improved tidal heating models, and you start to narrow down which interior structures are plausible. For now though, the truth is that we still do not have a clean answer. The distribution of volcanoes on Io is telling us that our current models of how tides deposit heat with depth, how plumes move it around, and how the crust channels magma are all missing pieces. The hotspots are effectively drawing a stress and plumbing map over the surface, and that map does not quite match anything we can compute yet. That uncertainty is not just a detail. If we cannot fully predict where volcanoes should appear on Io, with all the data we have, it means our understanding of tidally stressed interiors is still incomplete. And that matters when we move to exoplanets, where we will never see individual volcanoes at all. Getting Io right is the test. So the next step is obvious. To break this degeneracy between different interior models, you need more passes, more gravity data, more infrared maps, and ideally, a mission dedicated to watching Io's eruptions evolve in real time. That is exactly what the next part of the story is about. How Juno's final flybys and proposed future missions could force Io to either fit our models or break them again, and what that will mean for every other rocky world we study. How do you keep pushing a model until it breaks, then fix it, and then break it again? That's basically what the next decade of work on Io is set up to do. Right now, you're still in the Juno era. NASA extended Juno through September 2025 with the explicit goal of turning it from just a Jupiter mission into a full Jovian system mission, including repeated flybys of Io. Those close passes in December 2023 and February 2024, skimming to about 1,500 kilometers above the surface, gave you gravity, magnetic, and infrared data at resolutions we've never had before. Each flyby lets you update the interior model. You tweak crust thickness here, melt fraction there, adjust where the tidal heating layer might sit, and then you check whether that version of Io can reproduce the gravity field and the observed volcano distribution at the same time. It really is like getting repeated CT scans of a patient with a very aggressive volcanic disease. The first scan tells you the big picture. Yes, there's a partially molten mantle, yes. The crust is relatively thin. The next scans catch it during a flare-up, like the December 27th, 2024 super eruption that dumped an estimated 140 to 260 terawatts out of a 65,000 square kilometre region. Then you compare, did the hotspots flare where the stress models predicted, or somewhere else? Do the new lava flows match where your magma network model said they should come out? Every time there is a mismatch, you go back and change the assumptions about where heat is being generated, how it moves, and how the crust fails. So the immediate question is, what happens after Juno when that last extended mission data set is in and the spacecraft is done? Do we just stop at flybys? Inside NASA, people have been sketching the next step for years. The clearest version is the Io Volcano Observer, IVO, a dedicated mission concept built around Io alone. The plan is simple in outline. Send a relatively small orbiter to Jupiter, give it an orbit that repeatedly swings it past Io at a few hundred kilometers altitude, and make Io the main target, not a side bonus. Over a baseline of 9 or 10 flybys, with the possibility of more in an extended mission, IVO would follow the heat, measure how much tidal energy is being generated where, track how that energy is transported to the surface, and watch how heat and mass are lost to space. The instruments are designed around that goal. High-resolution thermal images to catch eruptions from both the day side and night side, a radar or laser altimeter to map subtle changes in topography as lava builds up or collapses, plasma and neutral gas analyzers to sample the mix of ions and molecules in the Io plasma torus and near the surface. The official proposals spell out 3 core questions. Where is tidal heat generated? How does it move upward? And how is Io evolving over time? Even though IVO wasn't selected in the last discovery round, the design tells you what planetary scientists want most: continuous targeted coverage of eruptions as they start, grow and fade, and precise measurements of interior and crust structure tied directly to those events. But even with a perfect Io orbiter, you're still missing something: the long baseline and the broad context that only telescopes can give you. That's where the synergy with big observatories comes in. Large ground-based telescopes have already been tracking Io's thermal output and plume signatures for decades. On top of that, the James Webb Space Telescope has now started to observe Io directly in the infrared, using instruments like NIRISS to resolve volcanic structures and even do interferometry on the disk. Those data sets give you something a spacecraft never can: consistent long-term monitoring across many years and eruptions from a stable vantage point. At the same time, Webb is being used on ultra-hot exoplanets like TOI 561b, where the best current explanation for the spectra is a thick atmosphere sitting over a global magma ocean. The same teams that are building and testing magma atmosphere models for those exoplanets are using Io as a nearby resolved test case. If your model can match Io's infrared brightness, hotspot distribution and sulfur chemistry under known tidal forcing, you trust it more when you apply it to a single pixel of light from a lava world dozens of light years away. So with Juno, with a Futrio-focused mission, and with telescopes you're building a multi-layered view. And every time a new layer is added, something breaks. That's really the core role of I.O. now. It's a stress test for planetary physics. Simple tidal heating maps said hotspots should cluster in certain latitude bands. The real volcanoes didn't listen. Simple crust models said mountains shouldn't be able to stand 17 kilometers tall without collapsing. I.O. built them anyway. Simple volcanology analogies from Earth said lava lakes should be a few kilometers wide. Loki Patera is 200 kilometers across and refuses to stay still. Then Juno comes in with a 260 terawatt multi-hotspot eruption and shows that some volcanoes are tied together over 65,000 square kilometers, while others right next door are not, implying a magma network that is partially connected and partially isolated at the same time. To make sense of that, you can't keep your physics in separate boxes. You have to merge orbital dynamics, tidal dissipation theory, mantle convection, fracture mechanics, volcanology, plasma physics, and atmospheric escape into one coherent picture. Change the orbit a little, you change the tidal stress pattern. Change the melt fraction at a certain depth. You change the conductivity and therefore the induced magnetic field. Change the eruption rate, you change the sulfur load in the plasma torus and the brightness of Jupiter's I.O. auroral footprint. Each discipline pulls on the others. I.O. forces you to solve the whole system, not just one piece, and that's exactly why the tension is not going away. The more precisely you measure I.O., the more ways it finds to expose the limits of your models. If Juno's remaining flybys and any future orbiter line up perfectly with a single interior scenario, that will lock in how you think about every tidally heated world, from Europa's hidden ocean to magma exoplanets hugging their stars. If they don't, you will have to admit that even in our own backyard, one small moon is still outsmarting our best theories. So the real question hanging over the next generation of data is direct and a bit uncomfortable. When we finally think we understand I.O., is that going to be because we got the physics right? Or because we quietly lowered our expectations of what a good model has to match? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.